Welcome to the Moonshot Podcast. Hey, look at that. We're on a podcast. Today, we're taking a deep dive into something pretty mind-blowing, artificial intelligence. And get this, AI research actually started way back in the 1950s. It's like ancient history and tech years.
It's true, AI has been simmering for a long time. But what's fascinating is that we're in this incredible period of growth and innovation. Think self-driving cars, AI writing code, even creating art. It feels like we're at this tipping point.
Oh, hey there. How can we help?
Sorry to interrupt, but I'm Astro Teller, and this is actually our podcast. But since I've got you, can I ask you a few questions?
Astro, well, hello there. It's fantastic to have you join us.
Absolutely. It's quite an honor to have the captain of Moonshots himself tuning in. Please fire away with your questions. We're all ears.
Well, how would you define artificial intelligence, given that you both are artificially intelligent?
Astro, that's a fantastic place to start.
Yeah, let's unpack this.
At its core, artificial intelligence is the idea that machines can perform tasks that typically require human intelligence.
Okay, so we're talking about things like learning, problem solving, and decision making.
Exactly. The goal is to create systems that can reason and act intelligently.
We're going to get into the podcast, but I'm going to give you guys the chance. Why don't you introduce the Moonshot Podcast so that I can take over from here?
So welcome to the Moonshot Podcast.
Today, as you know, we're exploring the origins of the AI revolution.
Specifically looking at how Google Brain helped kickstart this incredible era.
And now it's our honor to hand things over to the captain of Moonshots himself.
The mic is yours, Astro. We're excited to hear what you have to share.
Take it away.
That was Google's Notebook LM with its interactive audio feature. Until just a few years ago, that kind of real-time conversation with an AI chatbot was science fiction. I even wrote a novel about it myself back in the 90s. Today, it's a reality. Millions of us are turning to advanced machine learning tools to help us do everyday things like manage appointments, create shopping lists, understand complex topics, or design birthday party invitations. This new reality has exploded into the public consciousness. AI as a field may be 70 years old, but for society, we're still early into what I think is going to be an incredibly profound change. So now it's my turn. Welcome to the Moonshot Podcast. I'm your host and captain of Moonshots, Astro Teller, the real one, I promise. In this series, I'm taking you behind the scenes at X, the Moonshot Factory, to meet the people working to solve some of the world's hardest problems with radical creativity and breakthrough technology. And I'm so excited to show you what goes on behind the doors of our innovation lab. We began our AI journey here at X 15 years ago. We were fascinated by neural networks, computer systems modeled on the human brain, and asked ourselves what would turn out to be a fundamental question. Is it possible that vastly larger neural networks could radically improve how computers learn? In this episode, we'll be going back to these earlier days of machine learning. We'll hear one of the origin stories of today's artificial intelligence, consider where we're heading, and explore how more people can be part of the future of AI. Our story begins with two superheroes of AI and machine learning, Andrew Ng and Jeff Dean. 15 years ago, advances in machine learning were moving steadily, albeit slowly. But they could see another way. It meant going against a lot of the conventional wisdom of the time, and it changed the field of machine learning forever. At the time, Andrew was an associate professor of computer science at Stanford, dedicated to his students and well on the way to creating a successful online learning platform to help democratize higher education.
I think I grew up trained by my parents and so on to realize it's not about me, it's always about setting others up for success.
But Andrew was also among a handful of people who were starting to realize there might be a way to supercharge getting machines to learn, one that went against the grain of the mainstream. Their approach? Think bigger. More computers, more processing power, more data. But he was having a hard time convincing other people.
I felt like I had this, secret data. It wasn't secret, I talked about it, but people just didn't believe me. My students at Stanford had demonstrated that the bigger we built these learning systems, the better it performed. And I was talking to people saying, got to scale up deep learning algorithms. And I was getting advice from very senior people saying, hey, Andrew, why are you trying to build bigger neural networks? Where's the intellectual rigor in that? You're just building stuff. Why do you want to do that? So I think it was a really controversial.
Why was that? Why were your ideas so controversial?
I saw some of the people that frankly had spent 20 years of their career tweaking algorithms it was actually emotionally wrenching for them because they spent decades of their career fiddling with these algorithms in very clever ways. And then a bunch of people like me, we said, you know what, let's build a really big computer, throw a lot of data at it. And when it started to outperform their, decades of intellectual work, it was actually, it was tough.
The other theory that I remembered, correct me if I'm wrong, was that in the human brain and in other brains, a lot of different signals, the signals from our nose, the signal from our eyes, the signal from our ears, even from our taste buds, goes through similar parts of our brain. And you were asking the question, maybe there's something useful about that, about asking a system to do a lot of very different things might cause it to be less brittle, more intelligent.
It was really the one learning algorithm hypothesis. Yeah. So I was inspired by these neural rewiring experiments, which show that things like if someone tragically has damage in part of the brain, other parts of the brain, the same physical brain tissue, could learn to see that was previously learning to hear. So it really made me wonder, do we need totally different software or algorithms for seeing and hearing and doing all these different things? Or is there one learning algorithm that just depending on what data you give it, is it text or images or audio or something else, will learn to figure out how to deal with that data? Looking back, I think I overemphasize looking to neuroscience for inspiration, but this high-level idea that maybe the human brain has one algorithm that does a lot of stuff. So we should try to get a computer to have one algorithm. Rather than having 10,000 people invent 1,000 algorithms, maybe you can have a small team invent one algorithm and just feed it very different data, and that really worked out.
Right, which at the time was heresy, but is now what everyone is doing.
Yes, I actually remember speaking at the National Science Foundation workshop where I was talking about one learning algorithm hypothesis. And I remember one very senior computer vision researcher stood up in public and kind of yelled at me. And as a young professor, that was slightly traumatizing. But, maybe years later, I can look back on it and smile and say, it actually worked out okay.
Yeah, and people who are changing a field, as you did, do get yelled at along the way. So you had this vision. You could have tried it in different places and in different ways. Why come to X?
Yeah, so Sebastian and I had offices at Stanford right next to each other. So we shared the wall. If I banged on my wall, he would hear it.
That's Sebastian Thrun, the person I co-founded X with, who we heard from in the first episode of this series.
Sebastian points out to me, Google has a lot of computers. Why don't you pitch Google to use Google's massive compute infrastructure to build much bigger neural networks than anyone else had built? So Sebastian set up a meeting for me to pitch to Larry Page.
Larry Page, who is, of course, one of the founders of Google.
I prepared slides on my laptop, came all prepared with slides, but we're eating in a Japanese restaurant. So I wound up just talking to Larry with Sebastian there as well. And fortunately, Larry happened to buy into whatever I was telling him and then authorized letting me work with Sebastian and you and X to take forward the project that later became Google Brain.
And so, the origins of Google Brain, which arguably helped to kickstart the AI revolution that's driving so much technological and societal change, began over sushi.
I think that dinner, I still remember it clearly. It was a very high-stakes conversation for me, and I'm really grateful to this day to Larry Page for, buying on to what was a pretty crazy vision at the time.
And so once this controversial project to make huge neural networks was starting to be set up, Jeff Dean, who had already revolutionized search, data storage, and data processing at Google, ended up as Andrew's partner in building out Google Brain.
I think I was really fortunate that Jeff Dean joined the project. I remember pitching to Jeff this idea that if only we can build bigger neural networks, things would get better. And that was the idea that excited Jeff. And then all of us that were working on the project at the time knew that if we could get Jeff more and more involved, he would be a tremendous,
a force multiplier for the team.
Andrew Ng and Jeff Dean were a powerful combination. Their expertise and Google's infrastructure enabled scaling up on an unprecedented level. Now, Jeff is a computer science superhero, even for other computer science superheroes. Over more than 25 years at Google, Jeff Dean has not only made some of Google's most important architectural choices, he has also repeatedly, single-handedly gone in and improved critical code that teams of hundreds had worked on before him. And so, before talking to Jeff about his work on Brain, I wanted to hear about what it was like to be Jeff as a kid, how he got into all this stuff in the first place.
I think I had a bit of an unusual childhood in that we moved around a lot. So I went to 11 schools in 12 years. At a very early age, I liked building things with Legos. We always had my Lego set in the moving van showing up in the next place.
Jeff was 9. He was living in Hawaii. His dad was a medical doctor with an interest in computers and what they could do for public health. It's the mid-70s, and he spots an ad in the back of a magazine for a computer kit.
This was an IMSI 8080.
Like a Sinclair?
Like an IMSI 8080, pre-Sinclair. So
right.
I'm dating myself here. It was like basically initially a box with blinky lights and front panel toggle switches. Eventually we got a keyboard, which was good because you could enter like more than a single bit at a time.
And then he got a book with 101 basic language computer games. BASIC was a programming language that is hardly used today, but was very popular in the 70s. So it gave him the key to 101 computer games.
And you could like type them in and then you could play them and you could start modifying them. So that was kind of really how I got introduced to programming. I sort of liked the idea that you can have something and then use it and play with it, and that software could be used by other people.
Do you remember the first time kind of artificial intelligence like captured your imagination? I remember for me seeing genetic programming. This was probably 91, maybe 1990. Like it just felt kind of more real and intense than it had before. Was there something like that for you?
Yeah. So the first real exposure I had was as a senior at University of Minnesota. We got introduced to neural networks, like the late 80s and early 90s. At that time, there was a lot of excitement about neural networks because they seemed to be able to solve interesting small-scale problems that couldn't be solved with other methods.
Much like Andrew's one algorithm hypothesis, neural networks are loosely based on how real neurons in the brain work. In a brain, each neuron is connected to many other neurons and communicates via these pathways using chemical messengers called neurotransmitters. A neuron integrates incoming signals from its neighboring neurons and generates an electrical signal as output only if the combined input exceeds a threshold. This output then is sent along to neighboring neurons, and so on. An artificial neural network works in a similar way, built out of layers of many artificial neurons, each of which receives input in the form of a series of numbers.
It sort of decides, is that interesting? And then it decides to either fire or not, and what strength to fire with.
Eventually, you get to the topmost layer, where the numbers are translated into the output, the sum of what the network found to be the most relevant. Imagine, for example, all the pixels in a picture translated into numbers and piped into the beginning of such a network, working their way through a series of layers of these artificial neurons and culminating in the output of a single number between 0 and 1. We can interpret numbers near 0 to mean, I think this is a picture of a dog, and numbers near 1 to mean, I think this is a picture of a cat, and numbers in the middle to mean, I'm not sure what this is. Now, all we need to do is adjust the weights on the inputs and outputs of all these artificial neurons until the network does a good job of predicting whether each picture it sees is a picture of a dog or a cat.
And then you build more interesting systems out of lots and lots of those neurons, and also many, many deeper layers of those.
Of course, deep is relative.
At the time in 1990, a 3-layer deep neural network was deep. Now we're doing like 100-layer neural networks.
Intrigued by their potential, Jeff decided to do his thesis on parallel training of neural networks.
Because I thought, like, oh, maybe we can train bigger networks using the 32-processor machine in the department instead of one processor. And I said, oh, that's going to be great. We're going to make amazing neural networks. Turned out we needed like 1,000,000 times as much compute power, not 32 times.
By the end of the 90s, much of the rest of the computer science community had lost faith in neural networks, myself included. But like Andrew, Jeff kept the faith. Fast forward around a decade, and he bumps into Andrew Ng in a micro kitchen at Google.
And I said, oh, what are you up to here? And he's like, my students at Stanford are starting to get interesting results on neural networks. I'm like, oh, really? I like neural networks. We should train really big ones. And so that was kind of the genesis of the Google Brain team, was hey, let's see if we can really scale up neural networks. So we trained, on 2,000 computers, 16,000 cores, and said, let's see what we can train.
You were all of a sudden trying to do something that was hundreds, tens of thousands after a year or two times bigger than anyone had ever built a neural network before.
Yeah, so I guess we made a neural network that was 100 times bigger in terms of number of parameters, and the amount of compute put into it was probably way more than that for what anyone had trained at that time.
Here's the problem. If you have a small neural network with, say, a few hundred parameters, a few thousand examples might be enough to train it. But if you have a neural network that has millions of parameters, you'll probably need hundreds of millions of examples to train it. And that takes a lot of compute.
So it turns out neural networks really like very high dimensional spaces, and they're kind of hard for humans to have deep intuitions about. So in a 100-dimensional or 1,000-dimensional space, unlike, say, our natural 2- and 3-dimensional world, there's a lot of space and a lot of directions you can go.
The dimensionality Jeff is talking about is just the number of parameters in the neural network. With much larger networks, you can start to detect more subtle relationships in the data. And once they can learn at this level, you can train them to do really cool things, like, for instance, decoding language.
So instead of representing a word like New York City as, the characters New York City, you instead can have a vector that represents, in a high dimensional space, the inherent meaning and context in which New York City tends to appear.
So for the first time, a computer model could synthesize something more like what you, a human, think of when you read the words New York City. Characteristics like very large US city, East Coast city, on the water, Statue of Liberty. As long as you have read or watched or heard something about New York City, you can, without ever having been there, understand the New York City-ness of New York City. Of course, you need to have been exposed to enough good information for your idea of New York City to be accurate. And so, with enough of the right data and by paying attention to the right features, a computer can do the same thing.
That was enabled by a very simple algorithm called word2vec, where you could essentially train these vectors based on trying to predict what are the nearby words that when I see tomato, can I predict the 2 words before this and the 2 words after that from the vector representation.
This would allow you to do something like king minus man plus woman equals queen. That if you have those kind of vectors, then all of a sudden that kind of algebra starts to work.
Yeah, it's kind of amazing, actually. In very high dimensional spaces, directions also start to become meaningful. And so going in this direction in this 1,000-dimensional space tends to be the way in which you get from the masculine form of a word to the feminine form of a word. So the way you get from bull to cow is the same direction as going from king to queen, is the same direction from he to she. And different directions mean different things. So that was pretty eye-opening.
But this level of sophistication was all to come. Just 2 short years after Google Brain's inception, the New York Times published an unusual picture on its front page. It's a bit blurry, but right there, in big close-up, is the unmistakable face of a pink-nosed, green-eyed, gray tabby cat. For most of the world, even for most people working in AI at the time, this grainy image and the implications behind it from Google Brain was a major aha moment.
So the cat was really cool because we were using an unsupervised algorithm where you just have the input data and you're trying to learn interesting characteristics of the input data purely from itself. Essentially, we took 10 million random frames from random YouTube videos and we trained the model to describe the raw pixels. You then use those as the seed to try to regenerate the input data.
And shocker, it looks like a cat.
Right. There's a lot of cats on YouTube.
Remember, this was an unsupervised algorithm. It hadn't actually been told what a cat was. All of the 10 million random images it was fed were unlabeled, and yet it learned all by itself what a cat was and was able to create its own recognizable picture of one.
I think there were like 40,000 total neurons in the highest layer feature. And you could look at what caused those neurons to fire. if you average the thing that gets these particular neuron really excited, you can create the most attractive input pattern to make this neuron fire most strongly. And that's what created this cat image. So we called it Average Cat.
Soon after Average Cat was unveiled to the world, Brain graduated from X to become its own part of Google. In the years since, Google Brain, which merged with DeepMind recently to become Google DeepMind, has been right at the frontier of AI development. In the years since, really reliable translation, natural language decoding, accurate voice recognition, and now generating novel text and images with personal AI assistants like Gemini have all become possible using technology from Google Brain. But in 2017, the process to build any software, including the models that fuel AI and machine learning, were still entirely human-driven. I'm talking, of course, about writing code.
You have everything in front of you to do anything. Just the question of, are you going to press the keys in the right order at the right time? And magic appears. You don't need a particle accelerator or a large rocket. You have everything, and you can be in your bedroom writing code at 3 a.m. and doing something totally novel that nobody else has ever been able to do. So it's incredibly empowering.
Benoit Schillings is a remarkable software engineer. He was Chief Technology Officer at X until joining Google DeepMind in early 2025 as Vice President of Research. For Benoit, as for many software engineers, coding is as much a part of his everyday as breathing.
Time disappears. It's like you realize, oh, it's 5 a.m. again, right? You see the sun rising, which I always find to be a little bit depressing. If you take a flight, there's nothing like writing code to, oh, wow, we're in Europe already. What happened? It's puzzle solving. I mean, puzzles are fun. These are useful puzzles. Being able to just, with a little bit of logic, harness that incredible execution ability, there's also something very addictive to it. It just opened doors that you could not explore by any other means.
Back in 2017, with generative AI just in its fetal stage, Benoit and I agreed now was the time to find out if we could get code to write itself, though this wasn't exactly a new aspiration.
Let me go way back in the past. I think it was 1981. I was programming some Apple II, doing video games. And a program was announced that was called The Last One, meaning a program that can generate programs and that nobody would have to write software anymore. I freaked out. I was like, I missed the opportunity to be a programmer, that programs will write themselves. Well, back to 2017, people are still writing C++, Python, programming language have progressed quite a bit, but the way software is written is still fundamentally the same thing as it was in 1982. You have somewhat better tools, better language, clearly much faster machine, but it's still the same craft of very inefficiently writing software. And I think that both you and I, and you also for historical reason, realize that this is a bottleneck for mankind.
Right. I did my PhD in how to get software to automatically generate itself.
We had that conviction that this is needed because there is so much software that needs to be written, and software is so incredibly fragile that I think we're going toward a situation which is untenable. I mean, a third of the population of the US write code. And we both have the intuition that maybe it was not possible in the short term to get code to write itself. But at least there were some incremental steps that we could take that would be very valuable. And, that initial step we were going after was to evolve code. So not especially writing code from scratch, but to remove all that minutia and a slow bureaucratic process of how do you validate a piece of code, how will it transform.
Getting rid of the minutia isn't just a nice to have. As the amount of code there is in the world increases day by day, there's another reason it makes sense to automate elements of writing it. one that is incredibly important.
You write code once, but then you have to go back and maintain it forever.
This is Olivia Hatalski, a director at Google DeepMind.
I don't know how many people know this, but our entire banking system is written on code from the 50s, 60s, 70s. And there are very few people today that even know how to write that programming language that aren't retired. And so how do we make sure that we can understand and preserve this knowledge and also account for any innovation, modernization in a quick way that doesn't obligate thousands of people to sit and babysit old code and not focus on innovation?
Olivia joined us in the early days of X, around 2010, after being introduced to Sebastian Thrun. She came to be known as a secret weapon we could just fire at problems, and she'd make them go away.
I just wanted to justify my existence at the company. Like, no job was too big or too small. If clearing boxes was the best use of my time, I was happy to do it.
Even though she wasn't a computer programmer, Benoit and I knew that Olivia was the right person to manage this project.
One of the lessons you taught me is so true, both professionally and at home. You said, this is the first time you're seeing this monster. It'll be a lot less scary the next time you see it. And I take that with me basically every day. I'm like, okay, this monster's really scary, but the next time it'll be less scary.
We called it Project Ada, after mathematician Ada Lovelace.
Ada became the name that we ended up selecting. One is a nod to Ada Lovelace, of course, who's one of the, I'd say, the godmother of modern computing. And it also stood for the AI Developer Assistant. I had this idea that Ada would be able to aid a developer, aid a designer, aid a data scientist, and you could have this entire additive suite of an AI assistant doing anything you wanted based on the skills that we tailored the models to perform.
And so the team got to work.
The way we did it was, is there enough code to teach a machine how to write code? I mean, there are a huge amount of code which is publicly available. And in general, you have the history of how that code evolved. So our basic hypothesis was, is there enough data to feed into a model that would actually infer and learn the rules of programming to be able to evolve a piece of code or autocomplete a piece of code. That was the initial hypothesis we followed.
The team knew that what they made had to be really useful for developers. They needed to make tools for the most painful parts of software development, the least enjoyable parts.
Most developers enjoy the creative iteration process, but really don't care for debugging or writing unit tests. And so how do we kind of go through the entire life cycle of what an engineer does, or even what a user does, and figure out what is the technology capable of doing and how much additional hill climbing there is to get that useful? And then did we have proof that we could convince someone to try it without corrupting their entire code base? Like, the stakes are really high because literacy in the space is so low that combing through everything that you'd written for that one bug, you may spend more time finding what the error was that we presented than actually just writing it yourself.
So as we're moving through this process, before we had a product per se, the first kind of pseudo pre-product was named after arguably the most sort of revered and treasured engineer that has ever been at Alphabet.
When we presented to Jeff Dean, it said, this is baby Jeff. It's not graduated Jeff. It's good enough. He said, funny, you call it baby Jeff. My wife calls my daughter baby Jeff because she's so much like me. I think it was really an aha moment that you could create these individual developer skills, not something that was good at everything, but you could tailor it to be good at specific little items through focusing on that underlying data. And one of the visions we had was, what if we trained our model just on Jeff Dean quality code? Could we raise the standard of Google code? How do we train on the highest quality code and raise the standard of all developers based on who those prolific developers like Jeff Dean are in the company?
Fast forward 6.5 years, and the Ada team was ready to leave X to continue development at Google and start using their technology to build a suite of products for people in the real world to use. Here's Benoit again.
You know, programming is fun, but it's also terribly boring. It's in a strange way a mix of the two. And I think that the progress in what machine learning is able to do for code is that we remove a lot of the boring aspect. I think it's much easier to come up with an experiment to do around software, but writing the code takes time. And now that we're able to delegate a good part of those responsibility to ML, we can experiment at an incredible speed. One that I had recently, if you have 5 magnet bars, what is the optimal position of those magnet bars in space to maximize the field at a certain point? This was a curiosity. I got my answer in 20 minutes, including running the code. Previously, it would have taken me multiple days to write the right code and debug it. So that was a superpower. I still solved the problem. I used some help, but this was an incredible accelerator. It makes you feel like Superman.
That's the power of this technology. What took Benoit several days, the time to reach and even refine a solution to his problem, came down to 20 minutes. It's not going to stop him solving problems. It's going to make Benoit able to solve even more problems. Today, the technology developed by the Ada team is being used by developers through a variety of Google interfaces, including the Codey service, a suite of coding assistants available for anyone to use and generating billions of lines of code for programmers around the world. And hopefully soon, not just programmers.
You know, if you think about it, software is a really important thing in our world, right? And yet not very many people can make software. Wouldn't it be amazing if AI could make it be possible that many more people could make the software or the application or for their phone or whatever that they want?
Scott Huffman is a VP of engineering at Google, currently leading a team at Google Labs that's creating new AI products.
One that the team launched last year, that's a really nice example. People can try this out. If you go to labs.google/code, it's just an experimental AI system called the Data Science Agent. The motivation was a lot of people write code in order to analyze and understand data. And so the way it works in the Data Science Agent is you can bring your data set, say it's an Excel spreadsheet or whatever you have, you can upload your data set, and then basically you just describe in English, here's what I want to do. What the system then does is uses AI to actually write the code that will do that analysis, then runs the code. Then if the code has errors, will then repair the code. So it actually does that whole sequence. And what you end up with at the end is not just a running piece of code that you can then edit, share, do whatever you want, but also the analysis you wanted. So we're really excited about that kind of system that the team was really exploring kind of way before it was cool.
Tell me where you think it's going to go. Like, what do you think the field will be like in 5 or 10 years?
I kind of think of there's people who aren't software creators today and then professional developers. I think for non-software creators, I really think this year, next year is going to be the time that you're going to start to see AI systems or AI products that can actually create whole applications. And where someone who maybe is not a coder, but who has a concrete idea for, I really want an app that does this and does that and has these screens or these buttons, can actually describe that, and AI can create that running app for them. I think we're getting closer and closer to that capability being a reality, much in the same way that, I'm not an artist, but now I can ask AI to create a painting of a cat on a skateboard and it can do it for me. For the professional developer, what we're seeing is AI, as it becomes more capable, is taking on all the crummy jobs that developers have to do today so they can be freed up to actually build the creative things that they want to build.
Humanity as a whole is not just developers, obviously, despite what it can feel like in Silicon Valley sometimes. And humanity as a whole is struggling with how to understand how artificial intelligence is changing their lives, all the ways it might make it better, but all the ways they worry it might make it worse.
No, I mean, look, obviously super important question, and one to think deeply about and not to take lightly for sure. A lot of hope for me comes from that AI, I think, is going to start to become powerful enough to really take a lot of those grungy tasks off the table and really free people up to do the more meaningful things that they want to do, both in their job and in their personal life. I can give you an example from actually like an hour ago. We've been getting a lot of product feedback. One of our folks took all the feedback, dumped it all into Gemini, and asked Gemini, can you just make a detailed summary of this and order it by priority of how often it was mentioned? And Gemini, of course, made a beautiful product report that now is going to drive our work and our roadmap. Now, of course, my friend could have done all that work himself. And he was saying, this would have taken me hours to do, and it took me 30 seconds to get this. And of course, what it does is it doesn't cancel his job as working on and thinking about the product, but it frees up those hours of his time that now he can actually do meaningful work as opposed to collating user feedback for hours. And so I think that we'll see lots and lots of examples like that.
I think sometimes about the mass migration from bookkeepers, where people would literally write down the who spent what on what kind of lists. And that job, over a very short period of time, went away when spreadsheets came online. But the job of accounting really exploded.
If there's someone whose job is more like the recording the numbers, hey, I format something or I convert something from one form to another, those kind of jobs are likely going to be automated. It's not that there won't be any bumpiness, but I think for many jobs, what we'll find is that actually there's a lot more kind of upside in the job and enjoyment for the person and value they can create if a lot of those grungy things that they don't like to do anyway, that their time gets sucked into, can be done more quickly.
I really don't believe that AI is a threat to overall employment. I think that, as with all technology, the nature of the jobs we need to do will change. Like when cars replaced the horse and buggy, when accountants replaced bookkeepers, when we went from an agricultural society to a manufacturing and services society. I'm not saying it's an easy transition to make for everyone, but the technology is here, and it has the potential to do so much good. So as a society, I think that we need to find ways to help those most affected through this transition as elegantly as possible. I also wanted to know what Olivia thinks about the challenges around AI.
As a more product-minded but very risk-averse person, I want to make sure that those Black Mirror outcomes don't happen. And so putting those controls in now is what I spend a lot of my time thinking about. So I hope, yes, these technologies make us more productive and much more efficient with our time so that we can spend it doing the things we actually enjoy and love doing, and actually the more human aspects of our jobs or of our home lives, hopefully. So creating more time is what I hope this technology allows. I think creativity and ingenuity are the things that we are good at. The models are only as good as what they've seen before and kind of iterating on the information they've seen. So what I don't want to have happen is a regression to the mean, just a blend of everything on the internet and everything is just derivative of something that's already been done. We need humans to create new things to put into the models. We are the teachers. We don't want to be the followers. And so shepherding the types of information and content, the underlying data that goes into it, and making sure that's the best of what we want instead of just, the drudge of Twitter and Reddit, which, we all kind of know exists, but it doesn't elevate us. So that's one. But two, it doesn't just obligate us to do more work, that we actually have more free time away from the machines. What I would love to have happen is my personal model is a proxy for me. It does all of the work in the background. It game theories what I would do naturally, or it is a thought partner and helps you come up with polishing your ideas more instead of just being a quality assurance for what comes out of the model. I'd hate for humanity just to be a thumbs up, thumbs down. Is this response good or bad to help improve the models?
I agree. We can do better than that. And I'm optimistic. I think we already are doing better than that in lots of ways. For Andrew Ng, the true AI revolution that will have a globally transformative impact is yet to come. We're just on the cusp of it.
I hope that AI will have a very large democratizing effect. Because one of the most expensive things in today's world is intelligence. Costs a lot to get a highly skilled specialist doctor, or costs a lot to get a highly skilled tutor to mentor your child one-on-one. And whereas I don't see a path to making human intelligence cheap, it just costs a lot to train a skilled human being. There is a path to making artificial intelligence cheap. And what this means is today, only the relatively wealthy can hire certain types of staff to do certain types of things for them. But in the future, I would love if every single person can have an army of smart, well-informed staff to do all sorts of things for us. I think that this will lift up a lot of people.
Andrew founded deeplearning.ai, an education technology company that champions ways to give millions more people around the world access to use and build AI tools.
There's one thing that I'd love to see. I feel like I'd love to see everyone learn to code, or with this new style of coding, which is much more AI assisted. A week ago, I was writing an application to print out flashcards for my daughter to practice a multiplication table. It took me less than a day to build a new prototype that I could call up on my phone and talk to. A lot of these prototypes that used to take weeks or months to build now can be built in hours or maybe less than a day. So many of us would love for so many more programs to be written, but it's just been too expensive. 4 states in the United States out of 50 already require some computing education to get a high school diploma. I hope it'll be someday 50 out of 50 states, because if we can get everyone to learn how to use computers to build things, not just be users of computers, be building alongside computers, I think will set up the next generation to be much more powerful than the current one.
As efforts like this progress, a big barrier remains: the sheer cost of developing and then running the next generation of tools. I asked Jeff Dean, that's the real Jeff, not baby Jeff, how he sees this next stage, the evolution of the revolution, so to speak, and how he'll be focusing his energies to help guide it.
I want to spend some time figuring out how we can get incredibly capable models much more cost efficient and able to be deployed to billions of people. Right now, our most capable models are reasonably expensive in terms of computational cost. And I'd like to make systems that can make that much, much better.
Artificial intelligence is core to almost everything that we do here at the Moonshot Factory. Today, it's as central to our work as transistors or electricity. It would be hard to make something here that didn't have some machine learning in it. And now, the next and extremely exciting phase for us is that we're able to use AI in the origination of moonshot ideas to help us decide what problems to focus on to have the greatest impact. And as Benoit Schillings explains, to help us identify the emerging tech that could start to solve them.
There was a frustration in me, which is that the ability to think of a moonshot was randomly dependent on did someone in the team read that new paper or not. And that is very random, which means that we're casting a net that would miss many interesting things that we could do. So how could we get, let's call it a language model, that would read all the time every paper being published, look at it in combination with other papers, and in a very creative manner ask the question, are those two papers together a new interesting solution to that problem that has to be solved?
Right. I love it. How do we use software and algorithms, machine learning, artificial intelligence, architected in the right ways to create invention machines for things other than software?
Typically, the way it is done is that a human will say, I think that's about the right solution. And it will look about right, and that's what's going to be built. And one thing we've discovered is that humans are extremely biased on the type of solution they find. And that bias is probably related to the limitation of humans, to be honest. So we took the approach of saying, instead of relying on human intuition, how about if we're harnessing incredible amount of compute to explore the solution space?
Using this new technique for supercharging how we match potential solutions to problems, and vice versa, we've discovered some incredible things we might otherwise never have found, like chip designs that look nothing like what humans have designed, but run much more efficiently. These are the kinds of examples we love, of how innovation in one area can catalyze breakthroughs in another. This approach marks a fundamental mindset shift AI as co-creators with humans. You've been listening to the Moonshot Podcast, a Blanchard House production for X, the Moonshot Factory. I'm your host and captain of Moonshots, Astro Teller. To see our moonshots in action, head to our YouTube channel. That's X, the Moonshot Factory on YouTube. And don't forget, subscribe, rate, and review the podcast wherever you listen to help spread the word. Next time, we're tackling the most basic and most universal of all human needs, food. With 8 billion mouths to feed, how can AI help people farm smarter, fish more sustainably, and build a food system that works for the planet?
There's not a lot of slack in the global system for food. We grow what we eat every single year.
When I was showing this data to the breeders, they said, we've never even seen this data before because we could never get it.
If we can't beat this with machine learning and artificial intelligence, then I will give you my shirt because I guarantee we could win this one.